Okay, so for the homework, we started off with a binomial question where we have, so a biologist is tracking the spread of flu among college students in Southern California. She samples 6 students at a time, recording the number of 6 students in the table below. So the data that you had was just these 2 columns. The next step would be to calculate the total and fill in the rest of the table. You can't actually fill in this portion of the table until you do part B. So you could get as far as this XI, FI column. In this case, I defined a success as an infected student. You could have done uninfected, that's fine, but you would have to switch these P's and Q's. I calculated X bar doing the sum product divided by the sample size, so the sum product of these 2 columns, or you could do the sum of this XI, FI, which is the same thing as the numerator in the weighted mean equation, divided by X bar, or sorry, divided by your sample size, your total samples to get X bar. And that's the mean number of students infected per sample of 6 students. K is 6, that's how many students are being sampled at a time, the number of trials. P is probability of success and is equal to X bar divided by K. Q is 1 minus P, our probability of failure. S squared is our sample variance, which I mentioned in class. You have to transform your data into raw data and then use the var.s function to calculate it.
I have a question.
Yeah?
For the totals at the bottom of like the whole thing, you have 34 and then you have 93.
Yes.
I have every other like answers except I got 117. And like for that total, then the next one, shouldn't it be 1, the expected?
Oh, it should. You're right. Hold on. I probably missed. Yeah. There we go.
Okay.
There we go. Yep. Okay. Yeah, good catch. But yeah, so then you'd calculate sigma squared doing the X bar, the mean, times the probability of failure. There we go. I think I added an extra row at some point and it shifted everything down. So yeah, X bar times our probability of failure gets us our expected variance, sigma squared. So then you'd be able to fill in the rest of the table using the binomial distribution function because you have P and K. The expected frequency is our expected proportion times our sample size. And then the deviation is just the observed frequency minus the expected frequency. For C, what's the probability of 3 or more students in a sample being sick? That's just the sum of all probabilities for 3 or more students. So 3, 4, 5, or 6 students in a sample being sick. So the total probability of those possible outcomes. For question 2, 37% of the medfly population is brown and the remaining percent is gray. Suppose 12 flies were randomly caught. So right here we know that, well, it depends on who we define as success and failure, right? I defined success as brown, which means our probability of success is 37% or 0.37. Our trials are 12, so we randomly catch 12 of them, and we're asking what's the probability that over half are brown. So that includes, so that's 6, or I guess it would be 7. Oh, I see what I did. Interesting. That'd be probability that 7, 8, 9, or 10, 11, or 12 of them are brown. I did this by calculating the, I did 1 minus the cumulative probability of 6 and below. So I took the total probability, which is right 100%, and removed, like subtracted the probability of 6, 5, 4, 3, 2, 1, or 0 of them being brown.
I have another question. Sorry, can you go over sigma squared?
Yes. Like, what about it?
Yeah, like how did you find it?
It's just x bar times p. Or sorry, x bar times q.
Okay, thank you.
Yeah. For Poisson, the question is, a fisheries manager is concerned about the spread of marine lice in local population of parrotfish. She begins surveying the population and counting the number of lice on each fish. The results of her survey are below in this table. But first, I wanted you to fill out these values. Again, it's kind of a thing where you have to do a little bit of back and forth here. So the total number of fish is the sum of all, oh, sorry. Oh yeah, that is right. So for each fish sampled, there could be any number of lice on that fish. We've observed 14 fish with no lice, 25 fish with 1 lice, 38 with 2. So in total, we surveyed 167 fish. This XIFI, the sum then represents the total number of lice, the total number of individuals. And our X bar is again just the total number of individual lice divided by fish, and that gives us our average number of lice per fish. Filling in the table is very similar to using the binomial distribution. We use Poisson distribution instead with xi, x bar, and 0 or 1, but in this case we'd use 0 for all of these because we don't want cumulative probabilities. Expected frequency is just the expected proportion times n, and the frequency deviation is the observed frequency minus the expected frequency. And then I had this one extra credit question. If you were to sample 200 more fish, how many would you expect to have no more than 5 mites? That's just multiplying the probability, the cumulative probability of, oh wait, I think I did this backwards. No more, oh no, I did that right, okay. So that's the cumulative probability of having 0, 1, 2, 3, 4, or 5 mites times 200. That is the expected probability that a fish would have no more than 5 mites out of 200 fish. Are there any questions about the Poisson question?
I have a question.
Yeah.
Okay, I know it's an extra credit question, but I feel like it wasn't too clear because I thought it was talking about like adding the 200 to the number of fish that's already there. So I did 200 plus 167, and then I multiplied it to like the sum. Yeah.
Okay, that's fine.
Oh, is that fine?
I mean, it's not what I wanted, but I think that's like reasonable. Like
Well,
that's a reasonable way to interpret that.
I kind of like put 2 answers, so I did that one and like the one that I just talked about.
Okay.
Okay, thank you.
Yeah, you're welcome. Okay, are there any other questions about the Poisson? Okay. Let's see. Okay, so today we're doing, let's see, which, am I sharing the presenter view or the regular one? Like,
It's
can
the
you,
presented one.
I think presenter. Yeah.
okay, there we go. Okay, so today we're talking about normal probability distribution and z-scores. So we're switching gears a little bit. One of the central tenets of this normal distribution is the central limit theorem, which should hopefully be familiar to most of you. If you took like calculus at any point, the central limit theorem will also be familiar to you from that as well. It's like a very commonly used topic for calculus. The means of random samples from any distribution will have approximately a normal distribution, is what it states. And the approximation gets better with increasing sample size. And it's important if you're comparing samples from 2 or more different populations, because they'll all follow this normal distribution. And this is why z-scores and t-scores work and why t-scores are so often used. We'll talk more about t-scores and t-distributions. We'll talk a little bit about it today, but we'll really get into it after, I think, your first exam, which is, I think, in 2 weeks. But essentially we use z-scores when we have population data and t-scores when we have sample data. Our normal distribution is pretty much just this bell-shaped symmetric distribution. And we use it for continuous random variables, so lengths of fish or diastolic blood pressure of patients. If the values weren't continuous and they were discrete, we would have a binomial distribution. So here's one way to think about the central limit theorem using die. So suppose we roll one die 1,000 times and record the outcome of each roll, which can be the numbers 1 through 6, right? We would get a figure somewhat like this, right? Because we have a uniform distribution. We have a uniform probability of rolling numbers 1 through 6. So we do 1,000 rolls. We have, somewhere in this 150 to 200 or range of how many times we threw that die, and we get our respective frequency. So like the proportion of times we got each of those numbers. And we find that the mean is right around the center, 3.41, with a standard deviation of 1.73. Now, let's suppose we roll 2 die 1,000 times and record the mean of the 2 numbers that appear on each roll. So we'd add the 2 numbers and divide by 2. Now we'd get a figure like this. Because now we're collecting data on the averages of samples. And we find that on average, the sample mean is still around this 3.43 with a standard deviation of 1.21. So our standard deviation went down from the last one. And now we're starting to see this normal distribution bell-shaped curve. Now, what if we roll 5 die 1,000 times and record the mean of those 5 numbers on each roll? We get an even more defined normal distribution. and we have an even smaller standard deviation. So what happens to the shape when we increase our sample size? It begins to approximate a normal distribution. And what about the shape of, or the mean of the sample means with increasing n? They begin to approach the population mean, which is 3.5, right? So our means actually increased from 3.41 to 3.46 as our standard deviations decreased, right? Our standard deviation gets smaller, representing lower variation. So this is what distributions can look like, right? So we have a normal distribution, a uniform distribution, that would be rolling the die, and a skewed distribution. And this is kind of like a Poisson. But as we sample the means, we take means from these populations, and we then compare the means of those samples to each other. For all distributions, we get a normal distribution. The sample means fit a normal distribution, even though the population doesn't. And looking at this, so we have our sample means, we have our n equals 5, so our sample size is 5, our sample size is 10, our sample size is 30. And with all of these, we can see that as the sample size increases, our values, our curves become more and more normal, but they start to really pull in at the centers because standard deviation is getting so low and the means are really converging on the true mean of the population. So what's so important about this theorem? It allows us to determine the probability of obtaining a sample mean, assuming our sample came from a population with known mean and standard deviation. So those are the two things that we need. We need a mean and a standard deviation when we try to describe populations with a normal distribution. And with populations, we can do that using a z-score. And this is used to change a sample distribution into a standard normal distribution. Or I suppose that even this word sample is a little bit misleading. It's more like the way that we're going to use it, it's a population distribution. It's like you've sampled every single individual in an area and you know the true population statistics. But when we calculate a z-score using this equation over here, we're essentially standardizing the value. Because for a standard normal distribution, the population mean, mu, is 0, and the standard deviation, sigma, is 1. So we calculate our z-score with this equation over here, where x sub I is the sample variable at index I, mu sub 0, mu naught, is the population mean, sigma sub 0 or sigma naught is the population standard deviation, and z sub I is the z-score that we calculate. So let's take a look at this equation for a second. What it's actually doing is comparing each individual sample or an individual value or sample that we're looking at and the mean. We're seeing how far apart is this sample and the mean. And then we're dividing it by our standard deviation to calculate essentially how many standard deviations away from the mean is that value. And that's really all a z-score is. It's the number of standard deviations from the population mean. So if I have a z-score of 3 for a value, so let's say, actually we'll just get into that when when we do the worked example. It'll be easier to understand. But a z-score is not the same thing as probability. It's the number of standard deviations from the population mean. To get the probability of finding that value, you have to use the table at the back of your lab manual. It's on page 273. And you'll need to use that for your homework assignments and for the exam. So the table, if you flip to it and take a look, you'll see it up in the top right corner. You have a figure that's very similar to this one. So it's a cumulative distribution table. Statisticians have done a ton of research on this, and they've pretty much calculated every possible probability for every z-score. Yeah, and have all of that information in this table now. So the total area under the curve is 1. Again, if you've taken calculus, that will be familiar to you. The way I like to explain it is that if you imagine that this normal distribution is a closed shape and that's filled in, right? It's an actual shape. The area underneath of this curve and between this bottom line is 100% of the area possible, right? When we calculate a z-score, this is a number line. This is literally a number line with z equals 0 in the center. The mean equals 0. Here, let me grab. Okay. So this is the mean right in the center. That's our mu naught, and it's equal to 0 in a standard normal distribution. And then our standard deviation is sigma naught, and it's always equal to 1 in a standard normal distribution. So this is a number line. I feel like that gets lost in translation sometimes. This is actually a number line. We have values down here. Maybe this is 1, 2, 3, -1, -2, -3. So here we're saying maybe our z-score is equal to 1. Z equals 1. That just means that our value is 1 standard deviation from the mean. Let's go. No, we'll get there in a minute. Okay, so the area under the curve is 1. This value that we calculated, if z equals 1, the tables that you have at the back of the chart tell you the probability that lies to the left of your z-score, this blue area. The proportion, which is also the proportion of area under the normal curve. And that number, that probability, represents the probability that this value or a value less than that will occur. The probability that lies to the right, this white area over here, is found by doing 1 minus p for the area to the left. 1 minus the probability to the left. So a z of 1, if I look that up on the table right now, if z equals 1, the probability of that is 0.8413. So the probability of z equals 1 is equal to 0.8413. That's just on the table in the back. That's the area here. This blue area is 84.13% of the area underneath of that curve. If I want to know what the area over here is, it's 1 minus that. 1 minus 0.8413 That's the probability in this white area. That's the proportion of area under the curve in that white area. So when we read the table, the first thing that we do is we go down the left column to find the first decimal for the z-score. So we have, our tables look slightly different from this. It's pretty much the same thing though. So we have like, this would be 0, 0.0, 0, 0.1, all the way down to 1.0. So that's our like 10th place. And then next we go across to find our 100th place, like the second decimal point. So for 1.0, which is what I did, right? If our z-score was 1, I'd scroll down to 1.0. There is no other decimal, so it'd just be 0, 0 right there. 0.8413. And again, that equals this probability to the left, this shaded area. It's the probability of our z-score. And again, if I wanted to find the white area, I'd have to do 1 minus that probability. On page 87, there's a worked example. So a random value is drawn from a population with standard normal distribution. I'm telling you that the population has a standard normal distribution, which means that it has a mean of 0 and a standard deviation of 1. That's what that means. Standard normal distribution, mean equals 0. Standard deviation equals 1. So what's the probability that the observation will be less than or equal to negative 1.32? That's our z-score. So I can just look up on the table negative 1.32. And when I do that, I find that the probability is 0.0934. Here I've like drawn that out. So we have our mean equals 0, so our standard deviation equals 1. So our standard deviation would take us to maybe like here, negative 1. And then we have our z-score as negative 1.32. We're looking up the probability now to the left of that value, which is equal to this. So we're looking up the probability that the observation will be less than or equal to negative 1.32. That's this entire area right here. And this is our probability. For example 2, a random sample is drawn from a standard normal distribution. So again, we've got that our mean is equal to 0 and our standard deviation is equal to 1. What is the probability that the observation will be greater than negative 0.3 but less than 1.25? So if we draw that out, and I really recommend that when you do these problems, you have a piece of paper by your hands, and you can draw figures like this. These are really helpful to visualize this. Draw yourself a standard normal distribution with 0 as your mean, 1 is your standard deviation, and actually imagine where your z-scores are. So our z-score is negative 0.3, so that's right here, just a little bit to the left of 0. And then our other z-score is 1.25, so a bit further to the right. And we're saying, what's the probability that an observation will be greater than this but less than this? So we're looking for this probability between, this area between those two numbers. So we have to look up our z-scores for both of those, the probabilities for both of those z-scores. And we're asking, what's the probability that a value is greater than or equal to negative 0.3, but less than or equal to 1.25? That is equal to the probability of 1.25 minus the probability of negative 0.3. And that's because this 1.25, when we look that up on our table, gives us all of this entire area here. When we look up negative 0.3, we get this entire area. Because we're trying to find the area between these two, we're taking this whole area here and we're removing this bit. We're getting rid of this portion here, right? Because this white part here is the probability that the table gives us for negative 0.3. So we're subtracting that from the total probability of 1.25. And that then gives us the probability in between them. 0.5123 is the probability that an observation will be greater than negative 0.3 and less than 1.25. For example 3, a fish is selected at random from a population with a mean of 80 centimeters and a standard deviation sigma of 5 centimeters. What's the probability that the fish will be less than 75 centimeters? So our population isn't already in a standard normal distribution. That means that we need to translate these numbers from the actual population into a standard normal distribution, into z-scores. We need to calculate our z-score. So we have to use that equation from before where zi is equal to xi minus mu divided by the standard deviation. And we get that our z-score is -1. And that makes sense, right? If our z-score, if our zi is really just the number of standard deviations away from the mean that we are, that totally checks out. Our mean is 80 centimeters. Our standard deviation is 5 centimeters. We're asking for a value for 75. That's literally -1 standard deviation away from our mean. That's -5. Now we can look up our z-score, the probability of getting our z-score on the table, and we get 0.1587. That's the probability that a fish will be less than 75 centimeters, right? Because it's this area to the left. For example 4, we have the same population of fish. What is the probability that a randomly chosen fish would be between 74 and 82 centimeters? It's the same population, which means that our mean is still 80 and our standard deviation is still 5. But now we're asking for 2 values. So this is really just a mirror of example 2. That's really all it is, right? So before I gave you 2 z-scores, for example 2, if we go back, I said -0.3 and 1.25. So it was already in a standard normal distribution. For this question, the only difference is that the population isn't already in a standard normal, so you need to transform it into a standard normal. You need to calculate the z-scores for both of those numbers first. So we need to first change the value to a z-score for both of those, actually. So for sub 74 and z sub 82. So we're calculating a z-score for 74 and a z-score for 82. 74 is negative 1.25 standard deviations away from the mean, and 82 is positive 0.4 standard deviations away from the mean. Because we're asking for the probability between the two of them, we need to subtract the probability of the smaller number from the probability of the bigger number. Because remember, the probability of negative 1.25 is right here. That's what this is. But we don't want that. We want the area between these two numbers. And we find that the probability that a randomly chosen fish would be between 74 centimeters and 82 centimeters is 0.5132. Are there any questions about how to go about solving these?
No, not really.
Okay, it's pretty straightforward. It's not super difficult. There's no like Excel equations or anything like that. You can do all of these kinds of problems by hand. Because it's an online format, I'm going to show you in Excel, but it's all just using simple math. We can also look at the distribution of sample means. This is where it gets a little bit trickier. So again, according to the central limit theorem, the distribution of sample means is approximately normal. If we take a sample from a population over and over and over and over again, our means are going to be normally distributed. So for a set of samples, our standard deviation of the sample means is this. And this is actually just our standard error. Remember, we talked about this before, that our standard error is pretty much just correcting our standard deviation for sample size. And so sometimes you'll hear people saying that standard error is just the standard deviation of standard deviations. And that's what they're saying. Yeah, or the standard deviation of means. The variance and standard deviation of sample means is inversely proportional to sample size. So as sample size increases, both variance and standard deviation should get smaller. When we solve for these though, instead of dividing by standard deviation like we were before, we now need to use standard error instead. So looking back at example 3, let's say that this time we're sampling a sample of 10 fish. And again, our mean is 80 centimeters and our standard deviation is 5 centimeters. What's the probability that the mean of this sample of fish will be less than 75 centimeters? So now we actually have a couple other steps. We have to calculate the standard error using the standard deviation divided by the square root of the sample size. So our standard error is 5 divided by the square root of 10, and we have 1.581 as our standard error. We then calculate our z-scores using that standard error instead of standard deviation. So we've got x minus u divided by, or not u, sorry, mu divided by our standard error. So 75 minus 80 divided by this value we calculated before, and we get 3.163. Now we look up that value instead on the table, and we get 0.001. For having such a small sample, it's actually very unlikely that we would find a fish or a mean, sorry, the sample mean would be less than 75 centimeters. They would be, that would be, it'd just be very unlikely. We would expect with a small sample like this of 10, that our sample mean would be closer to the population mean. We're less likely to get extreme values to pull the standard deviation, or sorry, the sample mean down. Okay. Okay. So we've got some new functions. I want to get into all of this right now because we're not doing it until the next chapter, but the one that does matter is this calculation for standard error, which you've seen before. And it's just the standard deviation divided by the square root of the sample size. And you can use the count or you can type in the number of samples if you know it. Either is fine. Okay, so let's just go through these problems again. These are the ones that I just did, or I just went through in on the PowerPoint, but now we can actually calculate them. So it's the probability that an observation will be less than 1.32 standard deviation units below the mean. That is just looking at the probability that our, and I probably won't word it like that because it's not quite as obvious, that this z-score is then negative 1.32 because it's below the mean and our mean is 0. So we're wondering what's the probability of our value, a random observation, being less than 1.32. So the probability that a value will be less than negative 1.32. There's not really much for me to do in Excel or to really show you, because I just am looking this up on the table, right? So I'm going to our z-score on the left corner, on the left tab, to negative 1.3. And then I'm going across to 0.02. And I find that the probability of a value being less than that, of a value being less than negative 1.32, is 0.0934. And that's it. That's the probability that an observation will be less than 1.32 standard deviation units below the mean. And the standard deviation units, that's a z-score. That's the exact same thing as saying a z-score. For number 2, what's the probability that an observation will be within 0.3 standard deviation units below the mean and 1.25 standard deviations above the mean? So we're asking the probability that a value will be between negative 0.3 and 1.25, which is the probability of 1.25 minus the probability of negative 0.3. See, the probability of negative 1.2, or sorry, positive 1.2, when I go down to 1.2 on the z-score table, and then across to 0.05, it's 0.8944. So the probability of that minus the probability of negative 0.3. So going down, And then across, it's on the negative side. So you'll see for 0, there's 2 shaded ones. The one above is negative and the one below it is positive. So using the top one, the negative side of 0, to go across to 0.3. Oh, actually, never mind. It's just negative 0.3 with negative 0.300. So 0.3821. An equal sign before that. And that's our probability. That's the probability between these two. And I can draw that again. So that's the probability. We have like 1.25 here. And negative 0.3 here. If I was just doing the probability of negative 0.35, like what the value in the table is this area over here, but that's not what we want. We want the area between these two, and that's why we subtract the value or the probability of negative 0.3 from the probability of 1.25 so that we can get this area between them. If a fish is selected at random from a population with mu of 80, standard deviation of 5, what's the probability it will be less than 75 centimeters? So now we have to calculate again. We have to calculate our xi, which is 75, our mean is 80, our standard deviation is 5. We have to calculate our z sub I for the number 75. And it's equal to xi minus the mean divided by our standard deviation. And again, we get -1. This is minus 1 standard deviation below the mean. So now we can look up the probability of a value being less than -1 on our z-score table. And we find that it's 0.1587. For the example 4, you're selecting a fish from the same population. What's the probability that you would select a fish greater than 75 centimeters but smaller than 82? Sorry, my computer's freaking out. It like doesn't want me to draw this. But so our mean is 80. And then we're looking at 82. And 74. So that's what I mean when I'm saying that these are real numbers on an actual number line. It's not just, you know, kind of made up or whatever. And then we're going to, so that's what that would actually look like as raw data. We have our mean of 80, 82 is our upper limit that we're looking at, and 74 is the lower limit. We can then translate this into our z distribution by calculating our z-scores. It is just not cooperating. But essentially, right, we'd have our 0 would be here because a mean of 0. And we have to calculate the z-scores for 82 and 74. So our upper limit, our zi up, that's how I've called it, is 82. The lower limit is 74. Our mean is 80. And our standard deviation is 5. So now let's calculate the z-score for the upper limit. That'd be 82 minus 80. Or you can even, select it, divided by our standard deviation, 0.4. So 0.4. That's what I mean when I'm saying we're like translating this, right? Is that these things are equal to each other. This is just our normal population, and this is our standard normal distribution, I should really say. We're doing it for the lower limit, so now we've got 74 minus our mean divided by our standard deviation, negative 1.2. So that's this z-score value over here, negative 1.2. And we're looking for the area between these two numbers, which means, so we're looking for the probability that a value is greater than negative 1.2, but less than 0.04 in standard normal distribution language, which means that we need to find the probability of 0.4 and subtract from it the probability of negative 1.2. When I look up on the table, the probability that a value is less than 4 or 0.4 is 0.554. Right, wait, 6554 minus the probability of a value being negative 1.2. So I go to the table, go down on the left to negative 1.2 and across to 0.1151. Did I get that right?
What did you do for the low again, the equation? Mine's coming out different.
Oh, maybe that's why. Let's see. Divided by the mean divided by standard deviation. Your calc, you're getting a different z-score.
Oh wait, no, I just clicked the wrong one. Sorry.
Okay. Yeah, no problem. Okay. So yeah, we can calculate our z-score like that. Okay. And then we have our examples 2 and 3 again, but now we're looking at samples from a population. So we have to standardize for the sample size using the standard error. So standard error is equal to our standard deviation divided by the square root of our sample size. So now you are making 4 random observations and are interested in the probability these 4 observations will fall between negative 0.3 and 1.25 standard deviations units of the mean. So the probability that a value will be greater than negative 0.3 and less than 1.25. So first, let's calculate our standard error, which is our standard deviation. And I think this is the same population up here, right, where our mean is still 80. Yeah, our mean is still 80, and we're dividing by the square root of our sample size, which is 4. I think, no, wait. Oh, that's my bad. Not our mean, our standard deviation, which is 5. Oh, but actually, that's my mistake. This is a standard normal distribution, which means our standard deviation is 1. So in this case, we're beginning with a standard normal, so our standard deviation is 1. We can now adjust the z-scores to account for the sample size. So again, that means that we have to actually calculate new z-scores. So we're taking our upper limit, which was that 1.25, and we're dividing that by our standard error. Our lower limit is this negative 0.3, and dividing that by our standard error. Excuse me. So now we've got new corrected z-scores that we're looking at, and we can move on to finding this proportion. So we're going to do the probability of the value being less than or equal to 1.25 minus the probability that it's less than or equal to negative 0.6. And when we look that up on the table, we get 1.2 and then across to 0.05, 0.8944.
Is the upper limit not 2.5?
2.5. Oh, you're right. Sorry. It is. Oh, yeah. I'm sorry. I was just looking at the original one. You're right. This is 2.5. That's what we've just corrected for. So for the table, 2.5, 0.9938 minus the probability of less than or equal to negative 0.6. So we look that up on the table, 0.2743. And there we go. We got our probability that a value falls between those two. For example, 3, you were selecting 10 fish from a population with a mean of 80 and a standard deviation of 5. What's the probability that the mean sample of these 10 fish is less than 75? Calculate our standard error, which is our standard deviation divided by the square root of our sample size. And our z-score is xi minus mu divided by, in this case, our standard error, not our standard deviation. So we can look up this value on the table, but actually we can't. If you notice, you'll notice pretty quick that our z values only go from -3 to 3. So this value is more extreme than -3. It's smaller, it's less than -3, so it's not actually tabled. The smallest value represented on this table is -3.8. 0.09. And the probability of that is 0.001. So we know that this is even more unlikely, even rarer, even less unlikely to occur. So we can actually say that this is just less than 0.001. There's a smaller than 1 in a thousandth chance that in this sample of 10 fish, the mean of that sample will be less than 75 centimeters. Okay. How is everybody feeling about that?
Good.
Yeah. I feel like this is kind of a nice break after all of the other stuff that you've just been learning. But yeah. Okay, I want to make sure that we get to chapter 10, so I'm not going to go over this. It's really straightforward, though. It's kind of, it just breaks it down into a couple of steps. I think for 1 through 3, you just calculate these things. It kind of gets progressively more complicated, where for part A, you just calculate z-scores. For part B, you calculate z-scores and proportions. And for part C, you calculate the proportion between z-scores. Before your lab exam, I definitely recommend going over this on your own as extra practice. If you followed along with all of this and typed everything in, you won't have any problems here. Okay, so I'm going to let you do your group work for maybe 10 minutes, and I'll check in on your group so that we can get into chapter 10. Okay. So I made a note of this in the PowerPoint, but we're skipping inclusion intervals on page 96, necessary sample size for a specific confidence interval on 98, and confidence intervals for population variance on 99. For, you know, just so you're aware. So why do we need confidence intervals? We don't know the true population parameters, mean, variance, standard deviations. So we build an interval that we are some percent certain, usually 95%, that it actually contains the true population parameter. And it accounts for the error. It accounts for error, and there's always some error. So no matter how carefully an experiment is run. Yeah, so these are done for samples of populations. And it describes a region where we are X% confident, again, usually 95% confident, that it contains the true population parameter. And this is technically what that formula looks like, 1 minus alpha times 100%. And it's an interval surrounding our sample statistic where we are, again, 1 minus alpha times 100% confident that it contains the true population parameter, where alpha is the amount of error we decide is acceptable. Usually alpha equals 0.05. If that's the case, then we are 1 minus 0.05 times 100, 95% confident that our true population parameter lies in our confidence interval. So let's look at this example. If we take 20 different samples and build a 95% confidence interval around that, so we have our sampling distribution, the population here. This is actually the population where the mean is mu. And we take 20 samples and calculate the means. The mean is the black dot in the center. That's the mean of each of those. And the error bars, the standard error bars around those are the error bars. In this case, one of those samples missed the true population mean, right? Because that's kind of what our error bars are saying. It's saying like, oh, this is our mean, here's the error around it. All of these, except for this one, capture the population mean. This one completely misses it. So that's what we're saying when we're like, we're 95% confident that this interval includes the population mean. It means that sometimes, no matter how careful you are, you're going to miss it. For our z distribution, the standard normal distribution, we have to know the true population variance, which almost never happens. The calculation for the confidence interval is the same between a z distribution and a t distribution, except that this term in the center changes. It's our mean plus or minus our critical value, our z crit or t crit, times our standard deviation or standard error. Where again, alpha is our acceptable error, and alpha has to be divided by 2 because the curve has 2 tails. So this 1 minus alpha over 2 would be 0.975 for a 5% acceptable error. And that's how we would look up these critical values. Sometimes there's no 1 minus. It's kind of a weird thing where some programs have you enter it this way and other programs have you enter it this way. It's really, you just have to kind of figure it out. And I'll point them out in Excel. So z distribution versus a t distribution. Z distributions are for population while t distributions are for samples. Because it's a population, you have to know the population variance for z distributions, whereas for t distributions, you just know the sample variance. They are far more commonly used than z distributions because you almost never know population statistics. You almost never have the population variance, standard deviation, mean, all of those. So again, z distribution is for population standard deviation and t distribution is for the sample standard deviation. And this formula should look very, very similar. It's the exact same thing as calculating our z-scores, except now we're dividing by our standard error. So really it is the same thing as calculating our z-scores when we're using them for samples. So x minus mu divided by our standard error. Unlike z-tables, when we look up our critical values, as you'll see on page 274, you need to have the alpha and the degrees of freedom when you calculate the t-score. And again, our degrees of freedom is just n minus 1. And I think I have a table of that coming up. So it's very similar to the z distribution, but with a larger variance because our population variance is unknown. So we're accounting for that. As our sample size gets bigger, our degrees of freedom also gets bigger. As our sample size reaches infinity, the true population size, our sample variance converges on the population variance and our t distribution converges on the z distribution. And you can think about this as if your sample size, so let's say there's a population of 100 and your sample size starts at 30 and then your sample size is actually 40 and then it's 50, 60, 70, 80, 90, 100. Eventually your sample size is just the population size, and at that point you're just calculating population statistics. So this is what the table of t values looks like. Instead of having just z-scores, we have our degrees of freedom on the left and our our alpha values, our critical alpha values on the top. And they're called degrees of freedom because it's the number of values that are free to vary. And you can think about this if you have a sample and you're sampling them. It's like, it's a weird phrase, and sometimes it makes sense to people and sometimes it doesn't. And honestly, I still really have a hard time with it. essentially the idea is that if you have all these samples and you're looking at one of them individually, all the other samples are still free to vary. There's still variation between what the individual samples of your sample could be. It's kind of weird. The body of the table is, again, distances from the mean in standard deviation units. So it's the same thing as z-scores. It's just the table is set up a little bit differently. And you'll notice that as you increase your degrees of freedom, the value of t decreases, the number of standard deviations decreases. The confidence intervals for the t distribution, again, are the same thing pretty much as our confidence intervals for a z distribution, except now we have our t crit, which is represented by this alpha over 2, comma, our degrees of freedom. And that's really just a notation that tells you that's how you look it up in the table. So our confidence interval is equal to our mean plus or minus our critical value times our standard error. It's the same thing for the z-score. It's our mean plus or minus our z-crit times our standard deviation, or sorry, our standard error. And you need to know these equations when you're calculating your confidence intervals. Okay, so if a sample mean of 42 was found from a sample of n, a sample n of 12 bone lengths, and our sample variance is 16 centimeters squared, but the true population variance is unknown, how would you construct a 95% confidence interval for this distribution? Well, what do we know? We know our mean, our variance, our sample size, our degrees of freedom, alpha, and therefore we can look up our t-crit on the table. If we go to degrees of freedom for 13 on the left side and then across for alpha 0.05 or 0.5, or actually, so because this is something called a two-tailed problem, which means we need alpha in both sides. So we have total 0.05 alpha, but we have two tails that needs to account for. We need to account for the negative side and the positive side. So that means that when we're looking up our critical values in the table, we're actually looking at alpha divided by 2. So we go to 13 and then we actually go over to alpha equals 0.25. Because 0.25 is in both tails, that totals up to 5%, 0.05 for both tails. So we get our critical value is 2.160. And actually, unfortunately, I don't think I can draw that. Maybe I can. Maybe this will work. Yes. Okay, cool. So we've got our distribution and we've got our alpha values. We've got alpha equals 0.05, but we have two tails. We have these two values right here, which means that half of alpha has to go over here and half of alpha has to go over here. That's where we get that 0.025. Okay, so we have our t-crit, we have our t-crit, we have our mean, we have our standard, or we can calculate our standard error. So 42 plus or minus this 2.160, our t-crit, times our standard error, which is our standard deviation divided by the square root of our sample size, or it's just the square root of our variance divided by our sample size. When we do that, we multiply these two numbers together, we get 2.309. We now have to do 42 plus and minus that. We do minus, we get 39.391. When we add it, we get 44.309. Confidence intervals are written inside braces, inside these curly braces. This is important. I'm going to ask you to report confidence intervals, and I want it in this format. Unless I give you two boxes, which on some of them I do, and it's like confidence level upper, confidence interval lower, then you can write numbers in the two boxes. There are examples where I just have a single box and it just says, what's the CI? In that case, I want it in this format with these two curly braces. We're saying these braces say from this value to this value, from 39.691 to 44.309. That is the confidence interval around this mean. On page 100, there's another example. So a new fertilizer is being tried on a series of subplots in the area. The new fertilizer works well, but might impact soil pH, making it more basic. More basic soil is beneficial to nematodes that can decimate crop yields. So we don't want more basic soil. From a long series of studies, we know the mean soil pH for the region is 6.3. That's the mean of this region, the population mean of this region, because it's from a long series of studies. We know the mean soil for the region is 6.3. That's the population mean. We have 20 recorded pH values for these samples with fertilizer. So now we're adding fertilizer and we're trying to see what's the difference between the two. Construct a 95% confidence interval. So what do we know? We know that our mean is equal to 6.3, our sample size is 20, and our alpha value is 0.05. Because we're constructing a 95% confidence interval, that means the remainder is alpha. We need to know the mean, our t-crit, and our standard error. So we first calculate the mean and variance. This is the equation for sample variance. It should look familiar by now. Our mean is just the sum of all of them divided by our sample size, 7.11. That's our mean pH for the addition of fertilizer. Our sample variance is 1.2932. Next, we can use the variance to find our standard deviation and our standard error. So our standard error is 0.25428. Now we can go to our t-table to find the critical value that corresponds to an alpha over 2 of 0.025 with degrees of freedom n-1, 20 minus 1, 19. And we find that our critical value for t is 2.093. That's 2.093 standard deviation in units away from the mean. Now we can create the 95% confidence interval. So our mean plus or minus t times the standard error. And we get between 6.58 and 7.64. And I'm going to let you go in 1 second. I just want to get through this slide. So what does that mean? That means that we are 95% confident that our interval from 6.58 to 7.64 contains the mean soil pH after the application of fertilizer. The pH of the soil before application was 6.3, and that lies outside of the confidence interval. Therefore, evidence suggests that fertilizer has altered the soil pH, has increased the soil pH, has made the soil pH more basic, and therefore we must worry about the nematode outbreaks. So here's that data again. We have our soil pH and we have all of the things we need to calculate our confidence interval. X bar, we just calculate as our average. That's our sample mean. Our mu, we're told in the word problem that the mean for the region is 6.3. Our sample size is 20. And our standard deviation, we can calculate using the standard deviation dot S, because this is a sample of the population. Our standard error is equal to our standard deviation divided by the square root of our sample size. Our degrees of freedom is equal to our sample size minus 1. Here's where we get into the new stuff. On the new functions tab, we have this equation and this function, this t.inv parenthesis. And what goes inside of inv is 1 minus alpha over 2, comma, our degrees of freedom. And we use this function to look up our critical values instead of using a table. But it works the same way. So we can do t.inv. And there's actually this t.inv and t.inv2t, and you can use either of them, and I'll explain that a little more in a second. So the probability would be 1 minus alpha over 2, so 0.5 divided by 2, comma, our degrees of freedom. Which actually, I don't think that went through right. That's okay. We can just type it in 0.975. There we go. Yeah. Okay. So the reason, actually, let me see. Minus. I don't think that works. Yeah. That is fine. So you're going to want to just type it in 0.7975. So I like to think of this bit and filling in the alpha there as if we have a number line, a normal distribution, and we have 100 over here, or not 100 really. We should just 1. Sorry, this pen is also not working. Everything I own is breaking. So from 0 to 1, our mean is in the center, and we're looking at the alpha on either tail, right? Alpha is equal to 0.05. Alpha divided by 2 is equal to 0.025. If we think about this as a number line, that means 0.0, and we want 0.025 on either side. That means this number on the number line is 0.025. It means the number on this number line is 0.975. And this area here is half of alpha, and the area here is also half of alpha. We want to use the positive one so that we get a positive critical value. Because remember, this is, if we're thinking about standard deviation units, kind of switching back, this would be 0 standard deviation, or zero standard deviation units away from the mean. Because that's what our T and Z scores are, right? They're standard deviation units. How far in number of standard deviations are we from the mean? If we went this way, we'd have negative numbers. If we go this way, we have positive numbers. So that's why we use this number. So our alpha on this number line would be 0.975, and then our degrees of freedom. So we get our critical value, and then calculating the upper limit, we have our mean plus our critical value times our standard error. Our lower limit is our mean minus so we get our mean minus our critical value times our standard error. And there we get our range. I gave you two boxes here. I have critical upper, critical lower. If I just had one box, I would want you to type it as curly brace 6.577 or 578. Remember, 3 decimal points after the point, comma, 7.642. Close. For the question on 103, let's see, we have 200 eggs that are randomly chosen. So our sample size is 200. The mean weight was 0.824. Our standard deviation is 0.042. Find the 90 and 95% confidence limits for the weight of the salmon eggs. So our standard error is, again, our standard deviation divided by the square root of our sample size. Our alpha for the 95% confidence limit is 0.05, right? It's the remainder. So 1 minus our confidence interval. If we translate percent into our proportion or probability or whatever, or decimal, it'd be 0.95. So we would do 1 minus 0.95. That means the remainder, alpha, is 0.05. If we're calculating the alpha for our 90% confidence interval, it'd be the same thing. We translate 90% into 0.9 as a decimal. 1 minus 0.9, we get 0.1 as our alpha. So that changes the way that we're going to calculate our critical values. Our degrees of freedom is 199 for both of them, right? 200. We could also do it this way, 200 minus 1. So using the new function t.inv, and actually, I believe if you use this t.inv two-tail, you can actually just type in the alpha value, 0.05. I just want to try it to make sure that that's true, but I'm pretty sure that it is. Yeah. Okay. So when you have a two-tailed test, I actually recommend, I mean, it's up to you, honestly, if you want to use the t.inv, the regular one, and have alpha be 0.975, or if you use the .2t, which stands for two-tail, and use the 0.05, the whole alpha value, because the two-tail, the 2t, tells Excel, oh, we're talking about a two-tailed test, I should divide the alpha value. It already knows that because it's two-tailed, and when I say two-tailed, what I'm referring to is tail 1 and tail 2, it knows to split the alpha in half. So I actually recommend using the .2t version. And then our degrees of freedom. If we calculate the upper limit for this 95% confidence interval, that means we've got our mean plus our critical value times our standard error. Our lower one would be the mean minus our critical value times our standard error. Writing that out in the other way, it would be 0.818, comma 0.82830. For the 90% confidence interval with our alpha 0.1, we can use t.inv, and I'm going to use the two-tailed one. Our probability is 0.1. Our degrees of freedom is 199. Our confidence upper would be our mean plus our critical value times our standard error. For the lower one, we have our mean minus our critical value for the 90%. Make sure you're not picking these ones, times our standard error.